I've given like dozens of talks, but you can see I'm shaking, like because I'm a little bit nervous today because I found that the audience here is really technical. So I wanted to do something more in-depth than what I usually do. And usually what I want to do today, I usually take for that like an hour workshop, but now I compress it into like 20 minutes. So we will see if this works out. If I lose you midway, then that's my fault. It's definitely not your fault. So my talk is about Solidity internals. Quick introduction to myself. I'm Raoul Schaffranek. I'm the head of developer tooling at Runtime Verification. So we do formal verification and developer tooling mostly. For some of the work that for example, we did formally verify the deposit contract when Ethereum did the switch to proof of stake with our tools. Like this is where control was basically born. We are a long-term formal verification partner for Optimism and also a formal verification partner for Immunify Magnus. I see there's some Magnus people in the back there. Hi. And yeah, some of the tools that we've developed, maybe you came across one or the other tools. Just a quick overview, Symbolic is a Solidity debugger. That will be kind of the topic of today. But we also have Control, which is our formal verification tool. We have KVM, formal semantics, formal executable semantics of the EVM, and some other tools. So agenda for today is I'm going to talk about a new format that is called ETH debug format, or a new standard. It's called ETH debug. And I think, well, not everybody may have heard of it because it's still work in progress. It's still in the specification phase. So I'm going to give you an overview why this is needed. And then I provide a little bit of theory that is, unfortunately, I cannot get around it. We need to do this. And then for the second part, we are going to see the ETH debug format in action, how it makes developer tooling, developer experience better for everyone. And then finally, we will go really, really deep and reverse some Solidity compiler internals. And this is where I'm very nervous about. All right, so why ETH debug? Let's start with the motivation. Why do we need it? Well, we have an annual Solidity developer survey where we ask developers, hey, what is your pain points? And since 2020, every year again, debugging shows up as one of the most dreaded aspects of Solidity. And 2024 is not on this slide, but I can spoil you, it showed up again. So, and the goal is now, it should not show up next year again. Like we finally need to solve this longest standing developer experience problem that Solidity devs are having. And this is really what we're trying to solve here. Like it's really a hard problem that we didn't solve for years. And for example, why are Solidity devs complaining about it? And I don't want to call out this tool. This is great. This is the Foundry debugger. But the Foundry debugger has to work with the information that is available from the compiler. And at the moment, that is not very much. So when you use the Foundry debugger, you are actually looking at some really low-level details. Like you see like memory in hexadecimal numbers. You see a stack. You see the bytecode. And well, you can at least see which program counter, like which bytecode corresponds to which Solidity line. So that's something. But it's not ideal. Like people are not meant to read this. This is another great tool. This is a screenshot from the Tenderly app, and I use it daily. It's awesome. It's incredible. But again, this tool has to work with what the Solidity compiler can give us, and that's not very much. And that's why you see, like, well, you see a lot of low-level information here that is not really human readable. So, and we need to solve this human readability problem. So, and this is the status quo. So we have a problem because, well, humans are really good at reading and writing Solidity, but they are very bad at reading and interpreting low-level EVM information and bytecodes. On the other hand, our tools, they all operate on the EVM level. And trust me, tools are way easier to implement at the EVM level. But then these tools are having a really hard time to making the translation back to Solidity so that humans can read it. So this leaves us in like this unfortunate we live in a matrix situation. So how are we going to solve this with the ETH-debug format? Well, two things that you need to know. So developer tools that want to be developer-friendly and present the information, error information, or debugging information, or anything really, in Solidity rather than in EVM, they have to follow two things. So left-hand side, you have Solidity. Right-hand side, you have the EVM. And you have the compiler that takes the source code to the bytecode. And then, friendly enough, the compiler generates a source map that a debugger or any testing tool can take to map the bytecode back to the source code. So that's, when you remember the slide with the Foundry debugger, that's why the Foundry debugger was able to show you in which line of the source code it stopped. Now there's another thing that tools need to do, and that is they need to translate the runtime information back to Solidity. Like, you don't want to look at raw memory, you don't want to look at the stack or at the raw storage. That's all like hexadecimal numbers that doesn't make any sense. There's pointers in there that doesn't make any sense. You want to translate them back to your Solidity variables. Now, the problem is that we need a runtime map for that, and this is the missing link, really. The Solidity compiler so far does not give it to us. So this is why these tools can only show you the memory or the stack, but they cannot show you, hey, what was the content of this variable at this point in time. So this is the missing link. This is what the ETH-debug format is trying to solve. Context about ETH-debug format, I said it, it's a work in progress standard specification, and it's meant for compiler-debugger communication. It should solve the debugging problem that we are seeing. And it's led by Nick, who built the truffle debugger. So this guy really knows his stuff, so he's leading this effort. He went down like the rabbit hole before us. Unfortunately, the truffle debugger shut down, but luckily, Nick did not give up on this. So now he's trying to solve this problem for all of us. In short, mapping source code or mapping bytecode to source code is not enough. We also need to map the runtime information back to the Solidity information. So turn raw memory stack into Solidity variables, turn EVM stack frames into readable Solidity function call stacks, and identify the variables that are in scope. How is ETH-debug helping us? Well, it's giving us all this information. And the more important part is this information can now be retained even through compiler optimizations. Compiler optimizations is really what makes it all harder for the developer tooling providers to implement it. And one thing, well, we can, like, if you know Symbolic, the tool that I will show you later, the debugger, we can already decode local variables. The problem is this only works with contracts that have not been optimized. With ETH-debug, we can do it in the future, even on optimized contracts, which is what everybody does. And now, the other thing right now is how we did it in Symbolic. This took us a lot of reverse engineering what the Solidity compiler was doing. We looked at the Solidity compiler code. We compiled small Solidity snippets just to figure out what we wanted, what the compiler is doing. So, and then we implemented an algorithm to like decode a variable from the raw memory, and then the Solidity compiler implements a patch or the language changes, and suddenly what we've done, our reverse engineering effort, needs to be overthrown, and we need to start from scratch. With the ETH-debug format, this will no longer be a problem because the language and the compiler, they can keep evolving, but as long as the format stays constant, they are not breaking the debuggers. So there's been at least 3 debuggers that I know of that have been discontinued, and none of them are working anymore because of these breaking changes. So the debuggers that we are seeing today that are implementing ETH-debug, they will be there for a long time. Even if they are not actively maintained, I think they will be there for a longer time. And finally, it means debuggers and dev tools can share code. And now you're wondering, okay, why should they do this? Aren't they competing each other? And who would do that? And the answer is, well, we do at runtime verification. So we've implemented a library that's called ETHDebugPy. So it's a Python library. And it's a complete implementation of the debugger side of the ETHDebug format. Everybody can use it. It's complete. It's free and open source. We were lucky that the Ethereum Foundation sponsored us to awarded us a grant to do this work. So it's all open source. Check out this GitHub repository. The goal is, of course, accelerating this ETHDebug format adoption because it solves our developer experience problems. And then we want to provide a reusable library. So we think this is useful outside of debuggers. This will be useful for testing frameworks. I think this will be useful for Wake that we've seen in the talk before. It will be useful for static analysis tools. So this is a great library. And finally, the last goal is assist compiler teams with implementing the ETHDebug format. And actually, we found like a handful of bugs in the Solidity compiler implementation already with the help of this library. So if you're building a tool, check it out, use it. Contributions are welcome. So let's look. So this was the theory part. Let me check the clock. Oh, I went really fast. Am I going too fast? I can start from the beginning. No, I don't want to do that. No, I'm just slowing down. So because what's coming now, that's going really deep. So first of all, let me show you what our debugger looks like, and what hopefully most debuggers will look like in the future when they have ETHDebug. So now, this is Visual Studio Code. On the right-hand side, you see some code. You see our debugger paused here in line 49. And interesting thing is, maybe the more interesting thing is here, what is not on the screen. And you don't see any low-level information. You don't see like the raw memory, the stack, the storage. Instead, you see like the solidity variables. So you can see this parameter amount is set to 100. You can see who's the sender, who's the recipient. And this works for every local variable. That works for every data type. Everything that you can wish for. You never need to go back to looking at the EVM memory or stack. That said, I still want to do that today with you. I want to show you how you make sense of the raw memory to get a feeling of how difficult this actually is. So don't be scared by the next slide. There's pointers on it. So you've heard of dynamic arrays in Solidity. You've probably all used them. So I have a really small function here. And you see things are already getting really complicated on the low-level side of things. So we have a really low-level function here that is just taking 3 strings, and then it's concatenating them, and it's emitting a message. So where are these strings actually stored in memory? So, well, we can see them in the variables here, so you don't need to look at this. Still, I want to do it today once with you. So you can see the string hello is stored at this memory offset. This is the ASCII encoding of the string hello. This is the ASCII encoding of the string world. And this is the ASCII encoding of the string hello world. So, and then you see, well, there's another thing here, and that is a copy of the hello world string. You wouldn't have guessed from this code that the strings are copied like 3 times. Like you copy hello to this string, you copy it again into this string. So why is it? Well, you have one allocation for the greeting variable that's storing hello once. You have one allocation for the world variable. It's storing the string world once. Then you are concatenating them, and concatenating here is a copy operation. Even though it would not be needed, the Solidity compiler could optimize for that and just don't copy the data, but it does it. So you have this copy string. And then finally, we are emitting an event. So, and when we are calling this emit operation, the string, the entire string, is copied once more. So you see, this is the point is not to remember what's on this slide, so you can't forget about it. I probably forget about it in like the other day, the day after tomorrow. The point here is, even simple Solidity programs get complicated really fast if you need to look at the raw memory. And this is the debugger, the defx issue that we are seeing today. So let's look at some more pointer stuff. Let's look at a dynamic array in Solidity. So we have a dynamic array of strings. Even though the size is known here, or could be statically known, Solidity does not recognize it. It's still allocating a dynamic array for that. Again, I'm just storing 3 words in this string, in this array, and then I'm concatenating all the strings, and I'm emitting a message again. Solidity code, intentionally very, very simple. Left-hand side, low-level code, very, very complicated. So but you can see some stuff. Like you can see, OK, the array length is 3. We have here 3, you have a 3 here, and you have a 3 here. So this is where the array length is stored in the memory. And then the 3 following words are storing pointers to the elements of the array. So, and these are absolute pointers. We will meet a different kind of pointer on the next slide. But keep in mind, this is an absolute pointer. So I can just read off the address, which is, or the offset of the memory, which is 100. This points me to here, or 140 hexadecimal, pointing me to here. And this is where the string contents, or where the string starts, not even the string contents. If we look at this line, we will find at the end, dude, I'm shaking. You will find the length of the strings. So the string hello, 5 ASCII characters long, or byte. No, it's ASCII characters. It's bytes. It's bytes. String world, also 5 characters. String exclamation mark, 1 character long. And then this combined string, it contains an additional space, is like C characters long, which is 12. I think it's hexadecimal for 12. So you have a pointer pointing to the array element. On the array element, that stores the length of the strings, and the next word stores the string contents. OK, are you still? Can you still follow me? Nice. I like this audience. It's very technical. Yeah, it's nice. OK, let's look. Let's make things more complicated. How are strings laid out? Or how are dynamic arrays laid out in call data? So I just showed you how strings are, how dynamic arrays are laid out in memory, and you would think, well, in call data it's probably the same. No, it's not, and I needed to learn this the hard way, because when I implemented symbolic and this debugger, and I reverse engineered all this, and I did all this work, and I did it for the memory, and I was like, yeah, huge achievement, I finally made it. And then I tried the same algorithm for the call data arrays, and turns out, no, this is a completely different algorithm that I need there. So let's look at dynamic arrays in call data. So to do that, I just changed slightly the code. So we now have an external function here that's calling concat. It's taking a dynamic arrays of strings in call data now, and it's concatenating them and returning the result. We stopped here in line 25. So we know that we have all the parameters that we used in this call in our call data. So I opened the call data view here. The first 4 bytes are always the function selector in the call data in case of Solidity. So this is just the internal function name that the Solidity compiler gives to the concat function. And now things get tricky. So let me stretch. What follows is the next word in the call data stores a pointer to the first parameters, to the first function parameter. So in this case, we only have 1 parameter, but there could be more for other functions, right? In this case, we are lucky, only 1 parameter, so there's only 1 parameter pointer here. But now, this pointer, if you look at if we would look at offset 20, well, you wouldn't. You would end up somewhere in the middle here. That is weird, and that is because this is not an absolute pointer, but it's a relative pointer. And to get to the address where the parameter is actually encoded, we need to add this value 20 to hexadecimal 4. So this is the base offset, and this is the relative pointer. We add them together. We end up at offset hexadecimal 24. So this is pointing here. Now, this is the beginning of our array. And dynamic array, now we are lucky. The first word, once again stores the array length. So array length is still 3. So, and then, once again, we have 3 pointers pointing to the array elements. And again, these are relative pointers. So we need to add this number 60 here to this base address 64. I did not put an error here because then it would be all errors on the slide. So, but this is a relative pointer pointing us to this address, and then we can read off here the string length, and here we can read off the string contents. All right, so, and let me check if I have another thing that I wanted to show. Oh yeah, I do. Okay, small pause. Oh, there's a question, yeah.
Maybe on previous slide, the base offset was just 0.
In memory, you mean?
Yeah.
No, it's not. Like the base offset is always the offset of the word where this pointer is stored. So the base offset here is 0xa. Yeah, but yeah, you can think of it as in memory, base offset is always 0. So you turn basically you get a different representation. Yeah, but thing is, pointers in memory, they are always absolute. Pointers in call data are always relative to the base address. I don't know why they did it, but that's how it is. And unfortunately, this cannot be changed because ABI encoding is actually something that is standardized, that is used in production. Now let's look at something else. So from this slide, you may think that the array elements are always stored in the order that they appear in the array, but that's not the case, as this example shows. So here we are assigning the string, the second or the third item of the words to exclamation mark, and then only after we are assigning the string hello, the string world. And you can see this leads to here are the pointers, and they are crossing lines. Look at these these pink things. Now, what happens if we copy this array into the call data? And cool thing about call data is it untangles these pointers. Now, why is this? Why should you care about it? Well, it basically means that copying stuff from memory to call data is not a simple operation if you have complex dynamic data involved. The Solidity compiler needs to iterate over this array every time you copy something into the call data. And it's not just copying chunks by chunks, it really needs to do arithmetic. It needs to resolve these absolute pointers into memory pointers, so there's all stuff going on. And now you see, what's the point? Why I'm showing you this if all this is not needed in the future? Well, I don't know. I just wanted to nerd snipe you. So in the future, you really don't have to look at this low-level data. You can just look at the Solidity variables directly. So this was like really unneeded excursus into Solidity internals, but well, it said it on my topic, and you still showed up. Okay, some shameless advertising for this tool. It's called Symbolic, and this is just a list of my favorite features. So what can you expect? This tool is, first of all, it's free to use. You can just go there. It's partially open source. So this East Debug library, we completely open sourced it. The Visual Studio Code extension is completely open source. There's some bits that are not open source yet that we want to open source as we secure funding for them and kind of make it sustainable. Because, well, our company is also not running on Laugh. But this is the end goal. All our other tools completely open source. So what can you expect? You can set breakpoints. You can do step-by-step execution in the Solidity. Really, you can just step on Solidity lines, and not what you may experience from other debuggers is going from one event log or from some storage operation to the next or to the next external low-level call. No, this is really stepping at the Solidity level. We have full support for all variable types and data locations already. That means for unoptimized contracts. For optimized contracts, we have this ETH-debug library, which is implemented in Symbolic, but the compiler is not yet generating this information for us. It's still work in progress. So I don't know how long it will take them. I know that this team is busy, and they are they have a lot of people to work on this. You can inspect event logs. I didn't show that, but that's nice. If you want to, if you are nerd sniped, you can go to the disassembly view. You can see the disassembled bytecode. You can set breakpoints at the bytecode. You can inspect memory, call data, just as we did. You see that? And then one of my favorite features is time travel debugging. So this was really fun. So that means you can go backwards in your Solidity code execution. And this is, I implemented this because it was fun. But then this is, I think, one of the biggest productivity boosts that I had while Solidity debugging, because that means I never need to restart my debugging session when I accidentally stepped over the point that interested me. So I can simply set a breakpoint in, I don't know, on the first line again, go back. And this is really strong. So time travel debugging is really cool. Try it out. And then there's a symbolic execution mode, which is really advanced. And I don't have the time to go into that in any detail. But symbolic execution is basically one flavor of doing formal verification. And this is what my company actually focuses on. So we are, first and foremost, we are a formal verification company. Symbolic has a symbolic, like with an I and a K at the end, has a symbolic execution mode. Honestly, I don't remember why we choose this name. So this is the case because we are doing the K framework, and all our tools start with K or end with K. That's cool. I don't know why we replaced the I. That was probably just a typo, but now we stick with it. So symbolic execution is possible. That's a very cool feature. It's a very interactive way of doing formal verification, a very visual way of doing it. So it's essentially, it's not much more difficult than using a debugger. So I think this is a great way to onboard new formal verification engineers who've never used the tag before and get them just to work on it. This is, however, still an alpha, and this is only available to our commercial clients if they want that. Okay, so this is a QR code that links you to the website. Everything else is there. There's the documentation. You will see where you can download the tool. You can try, even it runs in your browser. You don't even have to install anything, but of course you can. Yeah, and that's everything I have. Thank you again. Once again, I'm so happy that so many of you stayed here for me with the last talk. And I know, like some of you guys, you just came for the ending ceremony, but that's okay. All right, thank you.
Yes. There you go.
How was it difficult to implement supporting of mappings? Because I think it is more like dynamic than like implementation of tracing arrays.
Sorry, I didn't get the first sentence.
Like,
implementing
how was hard to implement tracing of mappings in Solidity?
Oh, that's really hard.
Yeah, and I have also the second question. What will be the next features to this debugging tool?
Oh,
Thank
that's
you.
a great follow-up question.
Yeah,
Okay.
and thank you for your presentation. It is exciting.
Thank you. So mappings are really complicated data structures because you cannot just enumerate over the keys in the mapping. You can look up a key. You cannot enumerate all the keys in the array. This is a limitation that we currently have. We have a very cool solution where we actually never, so when you have a mapping, there's some key that gets cache-hacked, and this cache-hacking is a non-reversible cryptographic operation. So we cannot we cannot get the pre-image of the hash. So this is why it's so difficult to enumerate over arrays. We have a solution that we are playing around with, but I'm not sure if it will ever see the light of the day. But the solution basically is we never actually compute the cache hash, but we leave it some symbolic value, as some symbolic variable. That's something that's already working in the symbolic execution mode, but I'm not sure if we can port it back to the concrete execution mode. I don't have a solution to that problem. I asked a similar question yesterday in another talk where I expected somebody had a solution to that, but no, they don't. And then the follow-up question was, what are the next features to expect? One other limitation that we currently have, you cannot just debug any Foundry test case that you have. But that is what everybody wants to use it for. Everybody wants just to debug their Foundry tests. And the challenge here is very, very technical, but basically Foundry has Solidity cheat codes. These are operations that don't have a counterpart on the EVM. They are a hack that is implemented in Foundry, and we don't have the same hacks implemented in our debugger. So that's one thing that we needed to do. Symbolic execution mode, again, that's also something that we are working on and that we want to make public for everyone. And then, there will be a tighter integration with our formal verification tool, Control, and our cloud compute platform, so that you can actually run like compute-intensive tasks, not locally, but on our cloud compute platform. So this is what to expect. I cannot commit to any time frame. It always depends on on the funding that comes in, because again, our company does not run on love. We need to secure funding for every feature development that we do for that, and that's that's the more challenging part. More questions?
Do we have? Yes.
So you have to interpret EVM, right, to implement the debugger. Do you do it all in K? How does it work underneath?
The symbolic execution mode is using K. The concrete execution mode does not use K. It's using, actually it's pluggable, but it's using Anvil by default. We are about to make a switch to the Phoenix engine from the Build-Bear team, because they have implemented these Solidity cheat codes that we want, that everybody wants. The problem, why are we not using K for the concrete execution, is basically K is a complete semantics in terms of the really EVM execution, but it does not have semantics for the JSON RPC protocol. So this is the missing link there. We've started implementing that, so ultimately we want to move it all to K and connect it back, but yeah, not currently.